All right, let's jump right in. Today, we're going to build something pretty remarkable, an invisible shield that's designed to protect us from a threat we can't even see. We're going to look at the architecture of what's called a thermoluminescent dosimeter, or for short, a TLD.
And that really gets to the heart of it, doesn't it? This is the central question for this whole explainer. When the danger itself is completely invisible, you can't see it, you can't hear it, you can't smell it, how on earth do you know it's there? And maybe more importantly, how do you know how much of it you've been exposed to?
So to answer that, we have to start with the problem itself. Let's talk about the invisible danger, and really understand the world where a threat like this is just a part of the daily job. Think about places like hospitals, nuclear power plants, or high-tech research labs. You've got folks working around sources of ionizing radiation every single day. For their safety, it's not enough to just know radiation is around. They have to precisely measure their total exposure over time. We're not talking about one big event, but all the tiny doses that can add up over weeks and months and years.
Okay, so you've got this invisible culprit. What do you need? You need a special kind of detective, right? Something that can track its every move. So in this next section, we're going to meet our radiation detective and see exactly how it cracks the case. And here it is. This small, kind of unassuming little batch. This is our hero. The TLD is what we call a passive detector. That just means it doesn't need any power to work. It just sits there, clipped to a lab coat, silently and diligently recording evidence of any radiation that passes by. This little thing is the key to making the invisible visible. Now, the secret to how it all works is right there in its name, thermoluminescence. Let's just break that down for a second. Thermo, well, that means heat, and a luminescence, that's about emitting light. So what we have here is a material that after it's been exposed to radiation will literally glow when you heat it up. This one single, really cool principle is the engine behind the entire device. And at the very heart of that engine is one specific, super crucial component. So let's take a closer look at what we can basically call the magic crystal. This is the real core of the TLD. Now, this isn't just any old crystal you'd find in the ground. We're talking about materials like lithium fluoride or calcium fluoride that are engineered to have a perfect, specific internal structure, a crystal lattice. You can think of it like a perfectly built cage, one that's designed specifically to trap energy from radiation as it zips through. This little crystal is what makes the whole thing work. So how does it actually work? Well, the easiest way to think about it is like a tiny rechargeable battery. So step one, exposure. Radiation comes in, zaps the crystal, and knocks some electrons out of their usual spot. But they don't go far. They get stuck in these little energy traps in the crystal structure. At this point, the crystal is charged up with information. Then, step two, heating. Sometime later, back in a lab, a technician takes the crystal and heats it up. That heat gives those trapped electrons just enough of a kick to escape the traps. And that brings us to step three, light. As those electrons snap back to their original comfortable state, they release all that stored up energy in the form of a faint glow of light. And here it is. This is the most critical piece of the whole puzzle. This isn't just some neat science trick. It's an incredibly precise measurement tool. A super sensitive instrument measures the exact amount of light coming off that crystal as it's heated. And the intensity of that glow, how bright it is directly proportional to the radiation dose the crystal soaked up. It's a perfect one-to-one relationship. More light means a higher dose. It's that simple and that beautiful. So we have our magic crystal. Awesome. But a crystal by itself isn't a detector. Now we have to build the rest of the device around it. In this section, we're going to assemble the other key pieces. It's kind of like putting together Lego blocks, where every single piece has its own very specific, very important job. Okay, here's our blueprint. Of course, we start with the TL crystal. That's the heart of the whole operation. That crystal sits on a little metal plate called a heating plancher. You can think of that as the activator. Next, we add a set of filters, which act as a sorter. And this part is really clever, as you'll see in a second. And finally, we wrap it all up in a protective case, which is, the shield. Now, this is where the design gets really ingenious. See, not all radiation is created equal. Some types are less penetrating and mostly affect the skin. We call that the shallow dose. But other types are much more powerful and can go right through to our internal organs. That's the deep dose. So by putting different crystals under different filters, like a thin piece of plastic versus a denser piece of metal, the TLD can actually measure both of these doses at the same time. It tells us not just how much radiation was present, but also what kind of exposure it was. That's a huge deal. So let's put all those pieces together now.
In our final section, we're going to look at the complete dosimeter and see how it all functions as one perfectly cohesive unit. So you see, the real magic is how these simple parts work together. The crystal's job is to store the energy. The filter's job is to sort that energy by type and depth. And the casing protects the whole setup and, just as importantly, it has a unique ID number on it so you can link that specific dose measurement back to a specific person. Every single part is essential.
And there you have it. We've basically gone from a fundamental law of physics, thermoluminescence, all the way to a physical device that helps keep thousands of workers safe every single day. It's just a perfect example of how really complex problems can sometimes be solved with elegant and often surprisingly simple engineering.
It really makes you think, doesn't it? We took a physical phenomenon and turned it into a life-saving data point. It just begs the question, what other invisible forces are out there in our world, From tiny biological markers in our bodies to pollutants in our environment that are just waiting for an equally clever invention to finally make them visible too.